the Royal Society and the recipient of the Walcott Medal from the National Academy of Sciences of the U.S., the Charles Schuchert Award from the Paleontological Society of the U.S., the George Gaylord Simpson Prize from Yale University, honorary doctorates of science from the University of Uppsala and also the University of Hull. He's an elected honorary fellow of the European Union of Geological Sciences, Lyell Medal from the Geological Society of London, the Kelvin Medal from the Royal Philosophical Society of Glasgow, and the Ide and Luella Trotter Prize from the Texas A&M University. He is famous for his meticulous and groundbreaking work on Cambrian fossils. He's published 3 books, probably the most famous of which is The Crucible of Creation. And of course, he's been very prolific in his scientific work and has published close to 200 papers in leading scientific journals. Without further ado, I'd like to introduce Simon Conway Morris, 9 Evolutionary Myths, The Closing of the Darwinian Mind.
I think it's on that side, actually. Thank you. Great. Thank you. Well, thank you very much for that nice introduction, and it's a great pleasure to be here. I noticed that when I arrived in America, I was asked if I had any guns, and I said, of course not, no. But I do notice that our chairwoman here does have a revolver beside her, so I'm fully aware of the risks which I'm taking. Well, as you can see, in the English way, we think it's quite important to show flying pigs. But with regard to my thesis, I'm afraid it's not going to be very much about the fossil record and things like that. But I was actually delighted in the way that both Michael and Sandro mentioned, possibly inadvertently, the word myth. Because what I'm going to try and suggest very quickly indeed, if I can get through all of these, and that may be problematic, is in point of fact, there are a whole series of areas in Darwinian biology which are effectively myths. In other words, they're not fairy tales, nothing like that at all. These are unexamined basic assumptions about the way the world is. Now, I hope it's also the case that for those people here who are biologists, the things I'll be talking about won't actually be in any way exceptional. They may even possibly agree with 1 or 2 of them. The point here, though, is that so far as we're concerned with the debate, especially with religious fundamentalists, and that extends far beyond Christianity, of course, the sorts of things which are put forward in defense of Darwinian evolution seem to me to very largely revolve around aspects of the science where effectively the proponents of Darwinian evolution have, quite frankly, run out of things to say. And I think apart from anything else with regards to science as a whole, as Michael so brilliantly showed with regard to the insights into the genome, there's a vast amount of unfinished business. So let me start with the first of these 9 evolutionary myths, and this is the myth of the twig. Now, as we all know, and I think one of the most beautifully written parts in The Origin by Darwin is in fact his description of the evolutionary tree, and there's the whole tree of life, there's all these investigations into the nature of the relationships between the kingdoms and this sort of business, and it's encapsulated in this diagram here, where we do have not only the tree of life, but this whole series of diversifications, which I'll come back to in a slightly different context in a moment. But so far as, for instance, we in particular are concerned, then if we look at the whole of the tree of the life, which of course is largely entombed in the fossil record, it's all dead, we stand on a charnel house, of course, we are here, and the general idea, of course, is that here we are as bipeds, primates, mammals, vertebrates, etc., 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 but we are just one tiny twig in this enormous efflorescence of life which has been proceeding for the last 4 billion years. All of that is absolutely true, there's no doubt about that geometrically. What I want to suggest both here and in a later set of observations is the possibility, in fact, is that if you want to look at evolution that way, you're actually missing something which is is considerably more interesting. Now, I could take a whole series of examples. This is one I came across on my reading into examples of evolution within the amphibians, and this particularly includes a group of salamanders known as the bolitoglossines, these are plethodontids. And one of the interesting things they show, and this is based on David Wake's work in Berkeley, is they show this remarkable elongation. And this is achieved, not surprisingly, typically by just making more and more vertebrae. Now, there are all sorts of reasons why these animals become elongate, why they become burrowing, why they become almost limbless. And of course, there are parallel examples, both, for example, in the eels, wonderful stories there, and also, as it so happens, in the snakes. But the point about this particular example is in the phylogeny they were dealing with, and this is happily completely out of focus, what matters is, in fact, there are just 2 forms here which are known as a linear triton. This is a paper published in PANS in 2001. And in this particular example, what's happened is that the vertebrae are not actually produced in terms of multiple numbers to elongate the body. They actually adopt effectively a giraffe solution rather than the way that Sandro was referring to with regard to those magnificent African mammals. But the long and the short of it is, and this is what very much caught my attention in the quotation from this PANS paper, and I know this is an eyesight test, so I ask you all to get your opera glasses out, please. As they write, this is extraordinary, because this thing has evolved twice. So in other words, this species of linear triton, which was thought to be a single species, actually turns out to be two unrelated species, identical for all intents and purposes. This is extraordinary because the morphology of the single recognized species is extreme in its degree of specialization. Blah, de, blah, de, blah, there it all goes. Combination of characters and so forth. The adaptive significance of the linear triton phenomena appears to be local and limited. Thank goodness, that's a relief. Don't have to worry anymore. The salamanders displayed it can only be considered as terminal twigs on a bolitoglossine radiation. This, I think, is a very interesting statement from a classic Darwinian perspective. In other words, they're just twigs. It's just a local example. But, of course, as I'll try and explain in a moment, what happens if, as you descend through the whole of the tree of life, those decisions which lead to certain adaptive endpoints are themselves constrained, as they are in this particular case. In other words, if the solution appears multiple times, then it may be that actually what you regard as the end twigs of it are geometrically just that. But in terms of the configuration of the tree of life as a whole, it is possible that far from being a random arborescence, it actually has more of a determinate structure, which echoes perhaps in a way which Sandro would not agree with regards to what we look at as the structure of life as a whole. The myth of randomness. Well, I'll be talking a little bit about this tomorrow, but again, the neo-Darwinian mantra is, to all intents and purposes, life is contingent. It can go wherever you like. Well, this may actually turn out to be correct, but I'll try and very briefly persuade you why this may not be correct at all. Now, I will be talking largely about organismal structures rather than molecular structures. Classic example, of course, is the convergent evolution, and here's convergent evolution between the mollusk. This is a close relative of the earthworm, and here we are a close relative of the starfish, and as you'll all be well aware, the structure of these two eyes is strikingly similar. There's a whole set of very interesting stories to go with that. There are other sorts of examples which are particularly interesting amongst the insects. Here we have a honeybee, of course, and in terms of the evolution of eusociality, there are a whole series of very interesting stories which extend far beyond the insects to the mammals. And I think, in fact, now we are in a predictive framework of where we might find eusociality in groups where they have not yet been identified. But what's particularly fascinating amongst the eusocial ones, of course, is the evolution of agriculture. I took the train down from Cambridge. You'll know my country's a little bit behind the times, and this is the typical sort of view we have early in the year, in the normal sort of thing. I can't recommend my country too highly. But, of course, as you'll also be well aware with regards to the evolution of agriculture, this has independently occurred in a number of insect groups. Amongst the most famous are the leafcutter ants here. There's a minim protecting it from probably phoretic flies in this particular case, where they're cultivating these fungus farms. But also, in terms of insect agriculture, there's a fascinating example in what are, for all intents and purposes, the cockroaches, that is the termites, and they too have arrived at a fungal agriculture. Now, I shouldn't really tell you exactly how they build these supports to cultivate their fungi. There's a whole series of interesting stories there as well. But in the case of these termites here, it's turning out that there are a series of very interesting parallels between the leafcutter ant agriculture and the one which we see in the termites. But what is particularly interesting, I think, apart from anything else, is that although leafcutter ants, or rather the attine ants, developed agriculture perhaps 50 million years ago, the advanced agriculture only appeared about 10 million years ago, and it's about the same time as the case in the termites. And this actually has a bearing on various aspects about organization of the biosphere, whereby certain things which are relatively unlikely at one point in the history of the Earth actually, I think, become increasingly likely as you go through geological time. So again, they're possibly dealing with some unfinished business. But amongst the most interesting examples of agriculture are the ones which are much less familiar. They are, for instance, found in various sorts of beetles. But this is a particularly fascinating example because it involves this damselfish here, and this cultivates red algae. And interesting, in one particular species, actually it's happened more than once, they actually cultivate monocultures, and the red algae themselves are modified, so they are specific phenotypically to the fields which these damselfish protect from intrusion by other herbivores. And here there are, again, many parallels between these sorts of animal agricultures and human agriculture. So these are nice examples of convergences. They're also, I think, nice examples about why, in fact, fundamentally, I think it's highly unlikely that evolution is random in any interesting sense at all. The myth of simplicity. Well, on we rattle. Well, this again, yes, once upon a time there were bacteria, and now there is New York. Yes, quite. That's, we'll accept that. What I think, though, is a recurrent idea is that really primitive organisms are staggeringly, stupidly simple, and advanced organisms are fantastically complex. It's not as straightforward as that in a number of, I think, quite interesting ways. This is perhaps slightly peripheral to the argument, and you can already see that I'm taking my science far too seriously. Oh, yes, indeed. This is a useful slide. It's taken from a website known as Extreme Sports. But the point about it, of course, is here's this wretched mousetrap, and those of you who have the fortune to live in this country spend most of your time banging your head against the wall against these clowns who subscribe to intelligent design. And the idea is here we've got this irreducibly complex structure. What is interesting, of course, about this particular one is that the one which is often used in these arguments is a famous flagella motor in the eubacteria. It's a wonderful story of protein engineering, of course. What is somewhat less well known, in fact, apart from anything else, is that this flagella motor has evolved independently in very much the same way, and actually from a very interesting origin in the archaea. Now, the point about these complex structures is it's more than likely that there is a considerable degree of self-organization concerned with their evolution. And this, I think, actually underpins quite a lot of evolution, because, for instance, when we look at the evolution of the eukaryotic cell, there's a whole series of fascinating stories. I think I can now persuade some people that the evolution of a eukaryotic cell is inevitable for a whole series of reasons. But apart from anything else, when we look at what we infer to be, quote, the simplest sort of eukaryotic cell which first appeared, in fact, in a whole series of ways, it is surprisingly complex. And this has got nothing to do with a creationist argument or any nonsense like that. This is simply the observation, in fact, that when you're looking at these so-called primitive structures, they are not simple. And paradoxically, again and again, we find, as for instance, I think Michael might agree with respect to the genome of the more advanced organisms, that complex creatures like ourselves, in certain respects, are fascinatingly simplified. In other words, they're streamlined in all sorts of ways. So, again, all this is just an area which will cover many other topics of discussion. But what I'm trying to suggest is that the sort of general sort of linear view, cripplingly stupid, wonderfully advanced, is not quite as straightforward as that. Here's another one, the myth of, well, it will do. Well, this is true in a sense because we have a history, and there are all sorts of constraints on the way in which we are able to evolve. In other words, we have a burden of various things which allow us to do certain things with some facility, and other ones may require quite complicated decisions in order to continue to function from one state of organization to another. But I think, in fact, it is underestimated often, again, just how extraordinarily sophisticated biological structures are and just how good they are. I could give you a number of examples. This one I came across recently. There are now pretty good arguments, in fact, for example, with respect, no, I'm not going to talk about the toxins, unfortunately, but to do with the snake fangs here. These are as good as they're ever going to get. They are biologically perfect. This is not, again, an argument for creationism at all. It's just that they are reached the end of their capacity as a functional structure. But what is particularly interesting, this goes off into a whole series of other areas which I'll allude to very quickly right at the end, is that in certain aspects, we really have reached the limits of what is possible. Now, there are a whole series of areas of biology where this is being touched on. It's, for example, possible that in certain examples of crustacean tagmosis, there may be room for improvement. But in the case of the sensory system, and I'm particularly interested in this for a whole series of reasons, I think we can now show they are as good as they'll ever get. I've had to have some sort of picture. Here's a big noise. That's a jet going through the sound barrier, of course. Our ears work at a level of thermal noise. Our noses can smell a single molecule. Eyes can detect a single photon. In other words, these are sensory structures which can get no better because of the nature of the physical universe in which we find ourselves. This has a whole series of bearings, of course, about sensory perceptions beyond human familiarity, infrared, echolocation, things like that. And, of course, it also has an immediate bearing on the nature of science and the way in which our instrumentation allows us to see beyond these particular areas here. But, yes, nothing is perfect. But I would suggest this emphasis on us being basically a series of staggering mistakes where we suffer from a combination of piles and backache and all the rest of it, and heart disease, yes, they're true. But I think, in fact, they slightly miss the point. The myth of one molecule, one function. Now we're getting into slightly more dangerous territory here, because I think most biologists wouldn't think that this was a serious idea at all. But in terms of the defense of evolutionary biology, these sorts of things are put forward. This is one just rather trivial example, thing known as a beta-graspin fold. This thing shows a remarkable versatility. This is basically the same molecular structure, and as you can see, it is employed in a quite dazzling range of arrays. Now, actually, there's nothing particularly surprising about this. But to begin with, one might argue it would be interesting to know why these molecules are so versatile. And I think it's fair to say there's not been a great deal of inquiry into that area. There's also a related topic to do with what I like to call molecules of choice. There are certain molecules, for instance, in respiratory proteins, which are available. They're on the shelf. They are used, but practically never. Why not? They seem to be as good as hemoglobin. But I think beyond that, there's another aspect which slightly touches on what Sandro was referring to with regards to Evo-Devo, which again, I don't have time to defend here in any detail. But the general notion, if you've got one particular gene, it does something, and therefore you can identify what some in the trade like to refer to as, quote, a deep homology. And the famous example, of course, is to do with the PAX6 and eye development. And again, I don't have time to explore why I think this is effectively a fundamental misconstrual about what these genes are doing. But I think, again, it undermines, in the end, quite what evolution is all about. Ah, splendid, yes. Get out your bazookas. This is a good one. Oh, dear. The myth of cladistics, well, this is just a little sort of noir of mine. Not everybody gets so excited about it. Cladistics, as you'll probably know, is a standard methodology for understanding phylogenies, and effectively it identifies shared characteristics, which are, in a Darwinian way, of course, if you have more of them which are together, then you're more likely to be close related than if you have fewer which are shared between particular species, in a nutshell. And it comes with a whole sort of arcane terminology. The other thing which is very noticeable about this particular area of biological science is it's conducted with a complete lack of humour. I've never seen such a serious group of people operate at any time at all. Absolutely remarkable. So we can have a sort of classic example like this. You know, here we are. Here's a primate. Here's a canid here. And then we can say, well, sure enough, we're actually down there, if you like, and the carnivores are actually out there. And the cladistics will allow us to establish the nature of the canids, or the carnivorians, or the Afrotheria, whatever your particular group you want to work on. The reason why I think cladistics is so destructive is effectively for two reasons. And again, there's a whole lot of other territory covered in this area. Briefly, it's a brilliant method which doesn't work. And the problem is, in effect, that what we have are two things. First of all, it is extremely atomistic. In other words, it disintegrates the organism into a series of character states. And that means that it turns its back on functional integration, which is ultimately why organisms are so interesting. It can't deal with that. And equally, and this is something which I've come across in my experience trying to unravel small areas of the Cambrian explosion in terms of transformations, cladistics effectively is unable to deal with transformations where a certain structure is, in a sense, homologous, but is unrecognizable in, quote, two different phyla. So you can use cladistics if it makes you happy, if it keeps you off the streets and that sort of thing. It's a methodology which at least provides a testable series of frameworks. But I think in a certain way, it's actually fundamentally subversive to the sort of biology which at least some of us would like to do. Even better, the myth of missing links. Well, again, I was very pleased that Sandro showed Archaeopteryx, and I'll come on to that in a moment. Not for a moment am I saying that there are no missing links or any nonsense like that. What I very tactfully suggest is, perhaps the way we look at missing links, in a way, has been misunderstood. And let me give you two very quick examples, because this is our bread and butter. The historical evidence we have from the fossil record is instrumental in understanding how these extraordinary transformations of form actually happened in a historical context. And why this matters, of course, is we have such things as these wonderful examples, which Neil Shubin and Jenny Clack and others have dealt with regards to the origin of the tetrapods, and we can now establish that these animals were actually aquatic and that the limbs evolved underwater and were probably used as for ambush predators, for careful maneuvering through weeds and things like that. And only subsequently were they a pre-adaptation to come onto land in terms of terrestrial excursions and all the rest of it, fine and large. What has been slightly underestimated is because of the emphasis on these wonderful stories from the end of the tetrapod line, which is ultimately leading to a Canthostega and Ichthyostega, is in fact there are a series of other sarcopterygian fish which are also doing something rather similar. And amongst the most interesting is this group here, the rhizodonts, which are abundant in the Devonian and Carboniferous and could grow something up to 7 or so meters in length. Now, if we look at the phylogeny of these, what we actually see is here's the one made famous by Neil Shubin, Tiktaalik here. Here's our friend Acanthostiga. This is us for all intents and purposes. But there are two other groups, the Tristocturibdians, and you may have come across them. They include the famous Euthenopteron, but also much more interesting, here's our Rhizodonts in this fascinating form here, Sauropterus here. But the point is that this group and this group are effectively developing limbs, and in this case with fingers, independently of this group. Yes, the potentiality for all that is down there, but why I think this is so important is when we're beginning to unravel the nature, quote, of missing links. Rather than just having this lineal depiction where you go from A to B to C and D and so forth, where you have this sense that there's a sort of inevitability about it. There is an inevitability, I think, about it, but it's not in the sense of one story going there. It is effectively when you've invented something at this stage, then the invention of something like a limb then becomes an inevitability. And this is even more strikingly shown, I think, in the evolution of the birds. Wonderful group for all sorts of fascinating reasons, of course. But as Sandro showed, he showed the Berlin specimen of Archaeopteryx. They're only known effectively from South Germany, from Solenhofen, around about 150 million years old. Here are two Archaeopteryx. They're actually flying just above a swimming pool outside Stuttgart itself. I'm not at liberty to tell you why I know that, but it's quite true. And here we have an Archaeopteryx which is flying with two pteranodons there, fine and large. Now, we know that these are feathered dinosaurs, as Sandro mentioned, and we know, of course, that they fit into a general scheme of theropod phylogeny there. If you want a bit of orientation, this is Tyrannosaurus. That's the one which lives in the bottom of cereal packets, okay? And then here is Archaeopteryx, our friend here. But I've shown two more theropods here, also in red. Raja navis, Microraptor. Let's have a quick look at those. Here's Raja navis. It's a Cretaceous form from Madagascar, but it's a bird. It could fly. The other form, Microraptors, in some ways even more interesting. I expect most of you in this audience are very keen on bird watching, feed your birds in the garden, that sort of business. And no doubt if you saw this sort of thing in the morning, you would call the police. But Microraptor is a fascinating form, principally from China. And if we look at one of the species here, why this is so interesting is Microraptor actually has 4 wings rather than 2 wings, a whole series of stories about the origin of flight and so forth. But why all this matters is, of course, that we see that, in fact, flight has evolved independently 3 times within the theropod dinosaurs. That's actually not at all surprising for lots of reasons. First of all, theropods are bipedal, therefore they can free their forelimbs. Second of all, they tend to be quite small on occasion. Second of all, we know they have this propensity to modify their scales in all sorts of ways, probably originally for sexual display, but in any event related, in these cases, to the evolution of feathers. So you might say, well, that's fine and large. We get to a theropod here. We must not be surprised that we get birds. But so what? That's just a local instance. Just as with our Sarcopterygians, that's just a local instance. The problem, again, going back to the linear Triton phenomena, those amphibians, is how far down can you take that principle? And it now turns out, for example, that prior to the rise of the dinosaurs, there was another major group of reptiles known as the Archosaurans, and it now turns out that there's a whole series of fascinating convergences between the Archosaurians and the dinosaurs. And amongst the Archosaurians, blow me down, is here is one Archosaurian which is busy evolving into a bird-like theropod. So once again, the argument might be that when you get to a certain level of evolution, you must not be surprised that you reinvent the wheel. On with a couple more. The myth of mass extinctions. Dear oh dear. Of course there are mass extinctions, naturally. They're very interesting too. They're great to teach for all sorts of reasons. But do they quite do what people say? Let me recall, first of all, that of the 5 major mass extinctions, 3 did absolutely nothing. Hardly any difference on either side. The 2 which are really important, of course, the end Permian and the end Cretaceous. In the case of the end Cretaceous one, of course, it's famous for the disappearance of the dinosaurs. Why do we know that this scene here, the domestication of the dinosaurs, is an impossibility? And I should say in parenthesis, very unfairly, I like to call this slide here the degree ceremony in Oxford. Oh, yes, that's right, yeah. See all those dinosaurs? There's, oh, never mind. The reason we know this is impossible, of course, is because 65 million years ago, some clown dropped a large rock on the sky in June, if you're interested, at the locality of Shishulub. And as especially Gould, but also a number of other people, repeatedly emphasized, if those reptiles had not gone extinct, then we would have not had the disappearance of the, we would not had the rise, of the bats, we would have not had the rise of the cetaceans, and we'd have not had the rise of the primates. In other words, history was fundamentally rediverted into a completely new direction. Well, that, I think, is historically absolutely correct, but does it actually make any long-term difference at all? I don't think so, for the following reason, that in this particular case, we have the recurrence of ice ages. We know that living with the dinosaurs were the birds and the mammals, and that we know that they were already diversifying. My guess is that in a counterfactual world where the asteroid misses and the ice ages naturally still occur, what's going to happen? The net result will be that the diversification of the socially adept, tool-making birds and mammals are sooner or later going to spell the doom of the dinosaurs. The dinosaurs are not going to be with us forever. Why I think this is so interesting is that you can actually look at mass extinctions in a completely different way. The great thing about mass extinctions is they buy you time. Every time you have a mass extinction, basically you get about 50 million years for nothing. And that, in an Earth-like planet, may buy you as much as 500 million years of evolution for free. And the last one, and this is an absolute graveyard of ambition, but I wrote an article for the website of The Guardian, and in passing I suggested very politely that our understanding of consciousness and sentience were not likely to fit easily into any current scientific thought. And the response to this was, to put it mildly, interesting. People got extremely angry. I wonder why. Well, let's see if we can get that result. What's going on? This tissue between our ears, what's it actually doing in any sort of particular way? Where does our mind come from? Where indeed does our imagination come from, our ability to remake the world? Now, the standard scientific view is that for all intents and purposes, these are fairy tales. These are things which really don't matter at all. But I think there are a couple of lines of evidence which, in the end, will lead to any attempt to import simply a Darwinian explanation into this area. It's part of the story, to be sure, is doomed to failure. The first is, of course, that in terms of much more primitive organisms, such as, for all intents, here we've got a graveyard scene as yeast and Arabidopsis, fungi and plants, something like 30% of our genetic material is already available, which we use in our nervous system. There's nothing odd about that at all, because, of course, this is the basis of the chemical system which we employ in our nervous system. But a good part of what you need to make a nervous system is evolved long before there are any animals. Correspondingly, there are these very interesting experiments using the plasmodium here. Sandro showed us a maze experiment in a theoretical biology sense. These plasmodium can be used to navigate through mazes in a way which is effectively like that which is shown by a rat. They have bits of porridge they like rather than a peanut at the end, but the whole principle is exactly the same. The question which is so interesting about these things is, first of all, how do they navigate these mazes, but more especially, you can show that they possess, quote, a primitive intelligence, but they also possess memory. And that memory is no doubt chemical, but I think the interesting thing from this perspective is then to stand back and say, right, well, if that's true of them, and in fact these things are much closer to us than sometimes realize, where exactly does our cognitive capacity emerge? Is it simply adding on neurons? Is it simply adding them together into a brain? In which case this thing is an automatic emergence. And that, of course, is the standard mantra which is put forward by the great majority of people at the moment. But I myself am not convinced for a whole series of reasons. One of the reasons I'm not convinced are, of course, not to do specifically with the PET scans. I don't think they're quite as informative as people would like them to be. But these very famous examples where, in this case here, this woman has been very badly injured in a traffic accident in Glasgow. She's brain dead. The healthy subject has been asked to think about tennis or Wimbledon or something like that. And here's a brain-dead person. There's no activity in the brain at all. And here, as you can see, there's an activity going on. Now, this may not be actually a fair case because the woman in the end did make a recovery. She may not have been really brain-dead. But this is one of a series of lines of evidence to suggest that for all intents and purposes, if you think you're going to establish the basis of mentality simply on material processes, then I, with great respect, although I realize this is going to be deeply unpopular, and may be wrong, of course, but I think, in fact, you're not going to get very far with it at all. And in that respect, and this is something which goes into other territory, which is certainly highly controversial, though actually goes back some thousands of years in terms of the notion of what is the mind and what is matter and so forth, is one can actually look at the brain as being something more like an antenna, which again begs many sorts of questions. So, as you can see, I've travelled across an enormous amount of territory here. It would be extremely surprising. I see half the audience is left in disgust, but that's perfectly understandable. It would be perfectly reasonable that everything here I've said is complete rubbish. That's fine. But I do think that the general neo-Darwinian framework at the moment has entered into a closure. And I think the reasons for that have got nothing to do with the science. They've got nothing to do with the reality of evolution. They've got a great deal to do with the metaphysics of those people who are holding those particular views. So I shall shut up straight away. Thank you very much.
For our last 15 minutes of discussion, I think it'd be nice to just entertain a few questions for Simon Conway-Morris first, and then we'll get back to Alessandro Minelli for those of you who had questions for his talk. And then I'd like to have the panelists actually respond to each other's talks, and then I'll open it up to the floor for more in-depth discussion. So can we first start with any questions for Simon?
Thank you very much. Do I understand it that you're saying that there is a likelihood for certain forms to develop?
Yes, effectively. So yes, I think that there are various stable solutions, and there is an area of non-Darwinian biology which goes back to Darcy Thompson in particular, but also has been put forward by Brian Godwin and Stu Kaufman, which identifies particular islands of stability, and these things I think will emerge automatically. In fact, I think that's why convergence is so interesting. The stumbling point, and it may well be fatal to my theory, as somebody once said, is that there could well be particular transitions, like the origin of the eukaryotic cell, or the nature of the bacterial cell, or the nature of the nervous system, which are themselves effectively flukes. I think for a number of reasons this is now extremely unlikely, but nevertheless, that's where I'm going, yes, at the moment.
So you might say certain forms are not only potentialities from the beginning, but there might even be some kind of urge from the beginning towards the tetrapod form, or five-petal flower, or winged animal.
All one can say at the moment from the scientific basis is that if you go to look at the group which gives rise to tetrapods, the sarcopterygians, there are some very well-preserved fish which combine characters of the sarcopterygians with the other main group of fish, the osteichthyons. And effectively what is so interesting, I think, about the so-called missing links is that, and this actually has a whole, this occurs at all levels of evolution. There's a wonderful example from the cactus, as it turns out. What one actually has is, simplifying somewhat, that you have modularities which can combine in particular ways. And I think the interesting question is, are there rules of engagement for the way these modularities can combine? I rather suspect that there are a limited number of solutions there, in as much as though the combinatorial number in principle is very large, for various reasons, most of those won't work. So as you regress, you can sort of say, well, how likely is a tetrapod? How likely is a sarcopterygian? How likely is an osteichthyon? And we can get now down to the stage where you have something which is sharing characteristics with the chondrichthyons and the osteichthyons, where in a sense you look at it and you say, well, I'm not quite sure whether it's going to evolve into a shark, or I'm not quite sure whether it's going to evolve into a herring, because it has a series of characteristics there which will help to define either group. And this is what I think we see in the Cambrian explosion as well. If you want to read more into that, you can, but all one is saying really is that the opportunities in evolution are, I would suggest, basically not the question most things will work. It's actually almost nothing works, but what does work works extremely well.
Thank you very much.
Scott Lidgard, Field Museum. Nice to see you about 20 years ago. It's been a long time. Simon, I'll play devil's advocate from a rationalist point of view and ask you a metaphysical question. So if we assume that your argumentation for inevitability has to do with the number of consistent convergences that support the likelihood of certain solutions to problems being more than random, that's really a form of argumentation of an argument to the best solution that's tested by validation or verification. The number of cases that you can show, the stronger the case gets. So the metaphysical question for you is, we live in a particular plane in time. If we went back to some of those other times before those convergences occurred, could we accept your argumentation at all?
Well, touché. Well, the metaphysical response to that, I'm not a philosopher at all, it's very open. The metaphysical response to that, of course, is that yes, we could, because we know the rationality, the circumstances which allow that set of organizations to occur. So, of course, everything we're doing is post hoc in that way.
Right.
But in principle, what I think is particularly interesting, and I may be wrong about this, but there's this very nice paper by Adam Netzix et al. In PANS about the crustacean one. And there's a bit of room for improvement. But in quite a few areas, and this is true in some of the agricultural examples in the insects, those symbioses are probably as complex as they're going to get. In other words, this whole thing about the mutualisms, it's actually very subtle indeed. It's much more subtle than even was realized a couple of years ago. And of course, one can always stand back, a couple of years later and say, oh gosh, yeah, we've got some new evidence here. But again, it's a research program which is just sort of saying, well, prove me wrong. And I'm bound to be wrong. I mean, I always have been in the past. There's no reason I'm going to get it right this time, is there? But yes. But the metaphysics of it matter because, again, when one's engaging with the creationists and these people, most of the evolutionary biologists do not realize they have a metaphysics. It may not be, in my view, a particularly interesting metaphysics, but until they realize that, in a certain way, I think the common ground, well, I don't think it's common ground, but at least if you're going to engage with these sort of people, there's no point having, in my opinion, a shouting match. That's achieving nothing.
Agreed.
Thank you.
Thanks.